Good afternoon, guys. This is the Spiral Review for...
You already started recording?
Oh, man, I can hear myself echo.
You forgot to, you're playing it.
Let's try this again. Now I can't hear myself, except I can. That's still really weird. I don't have headphones with me, but that's okay. Okay, we're just going to deal with this. So, first problem is looking at 2x to the third times e to the 3x. And that's going to be a product rule. We need to do the derivative of the first times the second, which is going to be 6x squared times e to the 3x. And that's going to be added to the derivative of the second. The derivative of e to the 3x is e to the 3x times the derivative of 3x, which is 3, multiplied by the other function, 2x to the third. You don't need to simplify this. You can leave it like this. The tricky part about this problem was that it was a chain rule for the derivative of e to the 3x. So you get e to the 3x times the derivative of 3x, which is that 3 part.
Why did you do that?
There was a chain rule within the product rule for that one. I can't go back, but you can look at these online later tonight.
Oh, it's online? How do you...
This is going to be on my YouTube channel.
You have a YouTube channel?
Teacher Topher.
Why wouldn't you just do 2x times e3x?
2x times e to the 3x times the derivative of 3x,
So...
which is 3. That's that extra 3. Okay, second one is also a product rule. We have a cosine and a sine term. Each of these guys has something within it. That's going to be a chain rule within a product rule. So the first thing we're going to take a look at is the derivative of cosine of 3x, which is negative sine of 3x times the derivative of the inside, which is 3. Multiply that by sine of x squared. To that I'm going to add cosine of 3x times the derivative of sine of x squared, which is cosine of x squared, and that's going to be multiplied by the derivative of x squared, which is 2x. The whole answer is going to be sine of 3x times 3 times sine of x squared plus cosine of 3x times cosine of x squared times times 2x. The first term, I didn't say the negative, but there should be a negative there. If I zoom out a little bit, you can see it better. Okay? Our third problem looks like a quotient rule to me. And if we've got 1 over 2 cosine x, it's going to be the bottom times the derivative of the top. So 2 cosine x, the derivative of 1 is 0, minus the top times the derivative of the bottom. That's going to be negative 2 sine x, all over the bottom 2 cosine x squared. You can leave it like that. That is simplified enough.
So if it's in front of the sine x, the -2, you don't need to do the chain rule because the x isn't.
If the coefficient is in front of your function, you do not need to use the chain rule. You only need to use the chain rule if the coefficient would be inside the function. So if it was sine of 2x, that would be a chain rule. 2 sine of x is not a chain rule. Okay, for the sake of time, I'm going to skip to the next section. And I'll come back to that if I can. Here we're looking at graphs of f prime and f double prime. And I love the graphs I chose this time because they're really cool. I'm going to start with graph C just because it's the most bold out of anything that I see. And I'm going to look, and it looks like I have a horizontal tangent, one negative and one positive. And if I trace down from those two horizontal tangents, it looks to me like the same graph has a 0 at each of those points. Oh, there's a third horizontal tangent right in the middle. And that same graph, that's the thicker dashed lines, have zeros at all three of those points. So it looks like C, which is my bold graph, goes to B, which is my thicker dotted line graph. I don't yet know if C is the function or the first derivative. I don't yet know if B is the first derivative or the second derivative. I'd also like you to take a quick notice at the points where it looks like graph C goes vertical. Graph B has a vertical asymptote. So when C goes vertical, in other words, C has an undefined slope, graph B has a vertical asymptote because it's undefined there. That's pretty cool. Okay. Let's take a look at graph B. Okay, graph B has a horizontal asymptote at -1. That happens to coincide with the 0 for the other graph. It also has a horizontal asymptote at +1, and that coincides with a 0. So rather nicely, it looks like the lighter of the two dashed lines is A. We have C, which is our function. C has a derivative of B, and B has a derivative of A. You can use any of the reasons that we used to figure that out to explain your reasoning. Generally, the first thing you want to look for are horizontal tangent lines, and if they have zeros on their reflected graphs. Last thing I'm going to do is jump back to problem D on the first page, which is another quotient rule problem that's going to also involve a chain rule. First thing, let's set up our quotient rule. So it's going to be the bottom, 2 tan squared x times the derivative of the top, which is 12, minus the top, 12x, times the derivative of the bottom, 2 tan squared x, all over the bottom squared, 2 tan squared x. This is going to force us to take the derivative of 2 tan squared of x. The way that we might think about this as 2 tan of x squared. And that lets us use an outside function that's a power rule and an inside function that's tangent. I'm going to bring my 2 down, multiply that by the 2 that's already there, times the inside, which is tangent of x. And we're going to multiply that by the derivative of the inside function. So the derivative of tangent which happens to be secant squared of x. So the whole solution to this is going to be 2 tan squared x times 12 minus 12 times 4 tan x secant squared x all over 4 tangent squared of x squared. I'm going to skip the calculator section for now and jump straight to the trig. And here it looks like I forgot an equals 0, which will make this into an actual problem that you can do. And what we might want to do is look for things that we can factor out. It looks like in both of these I have a sine and a tangent. So I could write this as sine x, tan x. First one I'd have sine squared x. And then I'd have a minus 1. This is awesome. So I'm going to have sine x equals 0 from my first part. I'm going to have tan x equals 0 from my second part. And I'm going to have sine squared x equals positive 1 from my third part. Take the square root of both sides, I get sine x equals plus or minus 1. Something I need to be extra careful about in this problem that I really haven't focused on before is I'm only looking for the answers that are between 0 and pi, so not including 0 or pi. Sine is 0 at 0 and pi. Since neither of those values are included, I don't include those in my answer. Tangent is 0 at 0 and pi. Since neither of those are included, they don't count either. Sine is 1 at pi over 2. That looks like a number I can include. Sine is negative 1 at 3 pi over 2. That's not between 0 and pi, so I can't include that. The only solution to this between 0 and pi is pi over 2. For this trig problem, we factored, and then we found where each part of that was equal to 0. All right, the last section I think I'm going to have some time for now is going to be the differentiability part. One of the things I need to show differentiability, I need to show it's continuous. Okay, for continuous I need the limit as x approaches 0 from the left, and that's of 2x squared plus 2x plus 2. That equals 2. I need the limit from the right. The limit is x approaches 0 from the right of 2e to the x. 2e to the 0 is also going to be 2. That's nice. I also need f of 0 is 2. Cool, it's continuous. Is that enough to show differentiability? No, I need the derivative from the left and the derivative from the right. The derivative from the left is going to be 4x plus 2 evaluated at 0. That's an awful 0. It's getting worse. That equals 2. And then I need the derivative of 2e to the x, which is 2e to the x, evaluated at 0. That's a much better 0. Also equals 2. If you show continuity, if you show derivative from the left, derivative from the right, you have shown that your function is differentiable. Okay? The next thing we need to do is to find an equation for a line tangent to g of x at the point. I forgot the word at in there, that's nice. 2 comma 2e squared. What do we need to write the equation for a line? You need a point and a slope to write point-slope form. Okay? We have a point. We need a slope. How do I get a slope for a line tangent at x equals 2?
Find the derivative.
Sure, we got to find the derivative at 2. So f, or g in this case, prime of 2. Which function am I going to use? The 2x squared one or the 2e to the x one? How come?
Please pardon the interruption. Before the bell rings, we want to let all of the 10th graders know that all of your fundraising materials are in, and Miss Johnson, your class advisor, would like to see you throughout the day. Thank you very much.
Thanks, Mr. Stroud, for that lovely addition to the video. In fact, we do need the 2e to the x, because we're talking about where x is bigger than 0. Okay, so 2e squared. That's weird. So that's the slope. This is going to be a really strange line that you guys are going to hate, and that's okay. All right. So I've got y minus 2e squared equals 2e squared x minus 2. That's all I need to do. Last part of this is to approximate this function at the value 2.05. Okay, so y equals 2e squared plus 2e squared, 2.05 minus 2. In fact, as soon as you write that, that's enough of an answer for an AP Calc course. For our next topic, we're going to look at the function f of x equals ln of 2x plus 1. I'm going to find the domain of f of x. I know that for domain of natural logs, we know that 2x plus 1 has to be greater than 0. Only positive numbers can go into logarithms with a positive base. So if I solve for that, I get x has to be greater than negative 1 over 2. That's the domain of our function. F inverse of x, so if y equals ln of 2x plus 1, I'm going to switch my x and my y. X equals ln 2y plus 1. To get rid of the ln, I do e to both sides. That's e to the x equals 2y plus 1. So y is going to be e to the x minus 1 all over 2. The domain of anything that's e to the x, that's f inverse of x, the domain of anything that's e to the x is going to be all real numbers. There are no numbers that I could plug into e to the x that would give me a number that does not graph, or no real numbers. Next thing I'd like to briefly talk about is the calculator section. Really, I'm just going to mention the tricky parts about this. For the first one, the function tan squared of log of 2x, calculate the derivative at 0.2. The tricky part is typing in that tan squared. The way that we type that into the calculator is going to be the tangent function, the log function of 2x, double parentheses, and a squared outside. Your calculator is unable to read the notation that we use on paper. The second problem, the tricky part of this, is that we're looking at the third derivatives of f of x equals e to the 4x and g of x equals 2x to the third plus 3x. So I'm looking for f prime of x, which is e to the 4x times the derivative of 4x, which is 4. F double prime would be 4e to the 4x times 4. The triple prime would be 16e to the 4x times 4. And the derivatives of our polynomial would be first derivative 6x squared plus 3. Second derivative 12x. Third derivative is 12. So I'm looking for somewhere that 12 and the third derivative of e to the 4x are equal. I can use the graphing utility and find their intersection.